Okay, so okay, good morning, everyone. So today I would like to continue to discuss the last part on chapter 3. A few parts, and I think we can finish by today. So let me continue a little bit. Chapter 3, which is this the part that is discussing about the statically indeterminate structures. Okay. So the last discussion, we have this example. So we have a two element structure, element 1 and element 2. Both are fixed into the walls, and basically if they are the same cross sections, the same property as stiffness, and the difference is only the length, and to solve this structures, because we wouldn't know what will be the reaction force on each of the walls, PA and PC, then we need one more equations. We need one more equations to make all the solutions satisfy. And one equation that can be added is the E, the elongations, that we state that the elongation of material 1 and material 2, if we plus them, because we are fixed these two into the wall, so we would like to have the total elongation as 0. Okay, so there will be a slight changes in the between of 1 and 2, but at the end, at the very end, the total elongation it will be 0. So there will be one material that has tension, and the other one will be a compression. That will be our assumption, and we call this statically indeterminate structures, because we cannot really see what is the exact forces for each types of materials, okay, from the structure diagram. So if we try to solve this, and maybe let me just go here, we get that since we have this compatibility, we call these equations compatibility equations, right here, compatibility equations. And we can simplify this E, or actually you could directly write the FLAE directly into each one of them. Okay, it's also a similar results and definitions. But if you want to make more clean in your paper, you could imagine that there will be a small f that will define as the LAE, L over AE. Okay, that is the f. But basically, this can be done directly, and we could write here directly. This is basically the FLAE for each cases, F1, F2, and then the material 1 is only L, material 2 is 2L, and we can solve this, and we find that according to what we have here, from all the equilibrium that we can find, we get that let me just rewrite here so that we can connect this to the first equilibrium, which stated that the PA is negative F1 from this picture, and then PB or PC, let me write PC first, is equal F2. Okay, and then we could rewrite all in terms of PB. So 2PB over 3 if we solve this. So solving the first equations, which is the, or let me just write, this is going to solve that with the, with this one here. Let me just write here F1 LAE plus F2 to LAE. And simultaneously we can solve and get the F1 and F2 expressions we can get. I forgot one more to connect the PB. Okay. So we get this, and then we could take the assumptions, that is the total elongation will be 0. Okay. So we can see the UB, this one here. So if we assume UB is moving towards the right directions, which means that this one will be a positive, this one will be a negative. Okay, so that's why we take this positive and this one is negative, okay, as our assumptions. And then combining all the equations from what we have before, then we could rewrite the UB using the, actually this is the same as the FLAE, but we are going to use F as the this one. So basically that's how we get the UB. Okay. So the very strategic or very important equation is we need to define this total elongations. Okay. This we call as the basic force method. This is we call the basic force. But don't worry about the name, like basic force, or maybe there's another name for this method, because it doesn't really necessary to know which one you get, as long as you know exactly what the question is, and then the method and how to take these compatibility equations. I think most of the problem in the axial deformation you can solve. Okay. So how to take the solutions is basically we set up the fundamental equations, and then of course in this problem, the indeterminate structure, we are going to have unknown forces. Okay, which in our case, the previous one, we have the forces from the walls. Okay, that's the problem. So we need to get the geometric compatibility equations, which usually in terms of the elongations. Okay. And then after that, we solve simultaneously all the equations that we have from the equilibrium. Okay, so equilibrium and then the compatibility equations. Okay. So what you need is actually, you only need the equilibrium and then the elongations. Only these two that you need. Okay. But to arrange the formulations, that will be very tricky. Okay. So if you see the algorithm here, we start taking the equilibrium as we have. If you remember the statics part in chapter 1, we start by equilibrium. Okay, that we get the force directly, the forces equations, and then the deformation equations, the E. So this is F, this is E, and then from the E we get the compatibility equations, and then we have the unknown force that we can substitute. So basically we substituted for forces, and then solve through the compatibility equations, and then simultaneously we solve all the equilibriums, okay? And then we get all the results. Okay, maybe some examples on this part, and then I will show you the if we have time. Okay. Okay, I think we can try some example first. Okay, let me go for example. So let's say we have the load here. This is using the not standard units, but the thing's still okay. We have load P, okay, load P, which is the red color, that is load P. And then it's hung from the end of the rigid beam AD. So we have beam AD, which is supported by pin at A, and then also by two hanger rods, the 1 and 2. And then how much load can be applied without exceeding allowable tensile stress. So the tensile allowable we have defined here, and then another assumptions that we need is small angle rotations. Remember, small angle rotations means that when we have this, it's actually going to bend, right? It's going to bend the bar. But since it's a small angle, so it's supposed to be not this, but maybe a little bit deflected like this. But because it's assumption is small angle, so we just keep this as it is. Okay, keep this as it is, and we can use the triangle formulations. If you want to take this as you see that if you want to know like how small the angle is, we can take the tangent. If you want to, perhaps there is another question about the deflections, like how small the angle. Then we could get from the tangent if we know how much it will be, or how much the length will be. Okay. But anyway, since the question is only taking how much load can we pull, then we begin by taking the diagrams. And to begin this diagram, I believe from this expression, from this picture, we can agree that this AD will be our main frame. Okay? This will be our main frame. And then this one can be, we can take that as our tension or another reaction forces. This will be our loads. So we can draw that as our first diagram. So I will draw maybe around here. Okay, so we have A, and at A, it's a standard pin, so we have force at X and Y as usual. So we get AX and AY. Here is the P, and then this will be B, this will be C, and at B we have, let's say at B we have a tension here. Let's name this as F1. And at C we have another tension and naming as F2. and then all have a different distance. This is A, this is B, this is C. Okay, I think all clear. Okay, now we can continue to works. Okay, so we could see sometimes as you maybe probably have been familiar with, we could take the equilibrium starting with the sigma f or sigma m, and I think you better start with sigma m because you could get everything. For example, if we take sigma m with respect to this point, we can get the equations include the f1, f2, and p, right? And I think that is, I believe, needed, right? So we take the sigma m with respect to A, then we start to write and define the maybe this will be positive. So PC, right? PC, maybe PC like that, and then minus F1A minus F2A equals 0. So we have two unknown force, right? And then we could write also that since the hanger, the L1 and L2, suppose that these two are going to be extended. Okay, so well, the question should give you some information about that, but let me just assume that this will be going to extend it. So we are going to see that we are going to have additional elongation. So elongation at 1, which is the F1, L1, A1, and E1, and elongation 2. And from these elongations, okay, from these elongations, you can see that this will be going extended, this is going to be extended. So, like the assumptions for the small angle, so you start to imagine that there will be small triangle here, small triangle. Or you could taking this L1, A1, E1 first, you can compute and we get the E1 and E2 will be, this will be around 8 F1, this will be, E2 will be around 10. I think this is already rounded to several decimals. This is F2. Okay. Now let me take this as, so suppose that this is 80. Suppose that we have some small angle here. So this will be the E1 and this will be the E2. This is the new D. And this will be the A. This is B. Okay. So we could get the ratio for the triangle here, that the B over E2 is equal A over E1, or E2 will be E1B over A. Now this is, we take this as our compatibility equations. So compatibility equation is something that you need to assume and you need to make out by yourself. Okay, it will not show in the question. So you need to think how to get this, okay, based on the clue that perhaps the clue will be in the questions, something like assuming small angular rotations, which means that this will be, so it will still a straight line, which means it's not deflected like this, bang, like having an arc, but it's still a straight line, but deflected a little bit, but it's still straight line like that. So we have a small angle here. So which means that this small angle could make a triangle, a sharp triangle. It's not like this, okay, bend like this. If the angle is way too big, or maybe it means that maybe the load has maybe really high number, maybe it will be deflected like that. But since we are still in the early part of the mechanics, what we are going to have is basically related to statics and its equilibrium, which means the equilibrium, what we have here is that all is in a static form, which means all is equal 0. It's not going to like dynamic, right? There's two different, so in mechanical world, there is, first we say we have a statics, the second one we have a dynamics. This will be very different. Every time we have a statics, we can simplify everything, because everything is in equilibrium, everything is equal 0, all the sigma forces, moment, they are all 0. But in dynamics, sometimes in dynamics, you need to have like, you have the frequency, you have vibrations that will affect your all structures, and then there will be different simulation and models. But here, everything is, I believe, is simplified. This is the very first step. You get to know how the mechanical perspective of a structure will begin. It will begin. Okay. So now we get the relation between E1 and E2. Then we could solve this, okay, because we can substitute the E1 or E2, right? So we can solve this. Okay. And we can solve this F1 as F1. So let me write F1, 8. Oh, wait, wrong. And suppose that we are going to change the F2 with the E1 B over A. Or let me just write with the symbols without numbers. Okay, I think that's much easier. So let me write and take the let f1 is L1 A1 E1 and f2 is L2 A2 E2. Okay. So E1 will be F1 F1 E2 F2 F2. Okay. And then basically we get the F2 will be, we are going to exchange the E1 E2 with E1, so this will be E1 B over A, or this will be F1 B over A. Okay, so this is the second equations that we are going to take. So F1, so let me just write here just to mention that this is solved simultaneously with this. Okay, so exchange everything, the F1 and F2, so change everything. So we get the P, let me write PC minus F1A minus F2 is equal 0. So from this we get that F2 is PC minus F1A, and we can solve this and taking the F1 is AC F2 A squared F2 plus B squared F1, and then P, and then F2 will be BC F1. This will be the same. I'm skipping some process here, but this could be solved through the equations from the equilibrium. And then from the numbers here, we can substitute to get the F1 is 15 over 21p, and F2 is 24 over 21p. Okay. And then since we have another questions related to the allowable stress, let me make this a little bit smaller. Okay. So the allowable can be described by this stress definitions, and we get this is, and then divided by the A1, and then sigma 2 we can also divide A1 is 1 and A2 is half. So this is 1 inch squared this will be half inch squared. And then we could see from the numbers that sigma 2 is greater than sigma 1. So we set sigma 2 as our reference because it's greater than sigma 1. Then the P allowable will be taken by the sigma equal 24/21 P divided by 0.5 inch squared. So the P will be, so when the sigma allowable, how much is it? Sigma allowable is 30 ksi. So sigma allowable, so we are going to use the 30 ksi to get the P allowable, which is going to be 13.1 kips. Okay. So this is the final result. Now, of course, if we want to check the answer, since we have the F1 and F2, since we have this, we could check this two back to the compatibility equations that we set here. So we could check through here. We could put everything F2 and F1 and check whether they are equal or not. If there's one way to review the solutions. And sometimes in one question, there is going to be, sometimes there is only one equation, the compatibility equation, or it can be more than one. Okay? It can be more than one if they have like the structure can be more complex or a little bit complicated. Okay, now next, the second example. Okay, second example, and then we can finish this part. Okay, so the second example is we have three elements. So the first element is this. So it's like a rod. The second element is this outer shell, and the third element is the inner rod inside this second pipe. So it's like a pipe, like this one. We have the outer shell, the pipe, and we have the inner rod. Okay. So we have this structure. The element 1 is solid rod. Element 2 is a pipe surrounds the element 3, which is solid rod, and is identical to element 1. So element 1 and 3, they are identical, which means they have the same E. The same E. And then collinear in. And the three elements are attached at B, so attached here, assuming that this will be a rigid plate that is not going to deform. That's our assumption. And we can also ignore the thickness of this plate. We can ignore that. And then no external force at B. The three element assembly exactly fits between the walls A and C. and then we need to determine expression for the axial forces in the three elements when there is external force exerted at or applied at B. So when there is no external force, it will be going to be fit with the walls here, and then what happens if we pull some forces here? What happened to the axial forces, the expressions? So of course, to understand how the axial forces works, then we are going to have some principle on the axial deformations, so that we could know all the forces expressions. Okay, so we could state the diagram first. Let's draw here. So suppose that we are going to investigate the plate in the middle, because this is where all the elements are going to have a cross sections, right? We have one, we have 2 and 3 from the right, we have 1 from the left. So we have, imagine that this is starting PB. Okay. And then we could imagine when we have external forces in element 1, we have external forces going to the right. So to assume that there will be an equilibrium, we need to have some external forces at the element 1, which is going to be opposite with PB. We say that this will be the F1. Okay. And then we have another forces in 3, because the external forces are on the right and F1 is already on the left. We could have choices. We could make it right or left, but let me take this as going to the right. And then we have also the other part, which is going to equilibrium with the F1. This is symbolized the F2, because F2 is surrounds the elementary. Okay. So let me write here that the F2 is distributed around the pipe. Okay. Okay, now from this equilibrium, we get that this will be equal to 0. And we get from all the okay, I think we can okay, so let's continue for a while this part, and after that maybe we can have some exercise, especially reviewing what we are going to have in the midterm. To get you to what is actually the problem here in the chapter 3. So we could have what we call the statically determinate structures. Okay? And the second is statically indeterminate structures. So if we have here, we only have one equilibrium. So let me write here, we only have one equilibrium. Okay, and then the problem, we have three unknown forces. So we have more than one unknown force. So we have three unknown force. Which is F1, F2, and F3. So if this is not equal, we call this indeterminate structures, because that is not so easy to determine, okay? Because we need more assumption, more equations to solve these equations. If we have, for example, we have two equilibrium, we have two unknown force, then we can get everything. Okay? So since this is only having one equilibrium and three unknown force, we say that this is indeterminate. So we need some compatibility equations. And how to get compatibility equations? Let me write here to give you some notes. So compatibility equations. It can be from geometry. For example, some cases they have some relations between the elongations between the elements. Some cases they are mounted to the walls, that the total elongation is 0. That is one example. As we can see from here, that the compatibility equations could be from, if we take this as our reference, or here as our reference, then if we imagine that there is some deformations UB, so suppose that we have UB in the plate here. So when this is going to move slightly here, we see that the element 1 will be extended, and element 2 and 3, because they are on the same construction here, they will be reduced. Right? They will be decreased. So we see that from our assumptions that our displacement of the plate, this will equal to the elongation 1, but the elongation 1, it will be negative elongation 2 and also negative elongation 3. Okay, so we have, first is E1 is equal negative E2, and the second equation is E2 equal E3. So we have two compatibility equations that we need to solve to make all the equations satisfied. Okay. So if F is LAE, then we could rewrite this in terms of forces. So F1, F2 is, this will be F1, F1. And F2 equal F3, F3. And similarly, these two can be used for this, solving this. So we could perhaps changing all into F2, okay, that we have the F2 will be F1 over F2 F1 minus and f2 is also f3 over f2, f3. Okay. So we can use this to substitute the equilibrium that we have. So we have the f1 over f2 oh, this should be f1. So sorry. Let me write this in a more clear. Should be f1. So f1 is negative f2 over f1, f2, and f3 will be f2 over. Okay, and then we can change everything. So this will be f2, f1, f2 plus f2 plus f2 over f3, f2 plus p equals 0. So f2 is f2 over f1 plus 1 plus f2 over f3. Or let me multiply all with f1 and f3 so that we can get rid of the denominators. So this will be f2, f3, f2 So f2 is f2, f3, oh sorry, this should be f1, f3 plus f1, f3 plus f1, f2, okay, and then equal negative pb f1, f3. So f2 is negative f1, f3 over f2, f3 plus f1, f3 plus f1, f2 multiply with pb. Okay, and you can get the same result with the f1 or with the same way, the same method. We get the f1 and f3. Okay, so that's how we can get the expression. So the question is only asking what is the expression for the axial force in 3 elements, which means the f1, f2, and f3 in terms of the pb. Okay, so we get everything, f2, f1, f3. And with similar constructions, we can get everything. Okay, we can get everything. So yeah, I think the other part for our chapter 3 will be only about the thermal expressions, and the other part I think I will skip for a while. The other part will be, I think I will explain on the example and exercise. Let me check what else do we have. Yeah, I think basically we we can say we finished chapter 3. The other things is just the example. And then after we finish chapter 3, we can go for chapter 4. And there will be, aside from the midterm, there will be also a quiz, another quiz for chapter 3. Okay? Because if I put all chapter 1, 2, 3 into one midterm, maybe too much content. Because I think most of you haven't been taken the static course, right? So I think having only 2 chapters for midterms should be okay. Okay, I think we can go for our exercise. So exercise, I think I will prepare 2 questions, I think, from your assignments, and I hope everyone has done. I think everyone has sent the files. I have checked and see all your works. So I think I will discuss this with you. Okay, the first one is this pin jointed truss. Okay, there will be 3 questions or 2 questions. The first question is determine the reactions at the supports A and C, and then determine the axial force F1, F2, and F3. So if we take this, let me copy, and then I will take only the diagram. Okay, so if we see from the picture here, perhaps to make it clear, suppose that we have here is the F1, and then we have the at support C, CX, and CY, and then we have this weight W, right? And this will be, let's take this as our macro structures. So there is AX here and also AY, but I will take this F1 as our tension force, okay, as our tension force, and I will take the sigma moment at C to get everything from the to get the F1. Okay, so I will take the sigma moment. We take the respect of the C. So if C is here, then these forces can be easily compute the moment from this W. Right? And this part, the F1, we need to make it at least in the horizontal forces, as a horizontal forces. And how do we make up that forces is basically through this length. this one here. So this will be 2.4 and 3. We can take the triangle. And then the distance will be 6. So this will be, let me write here, that if we have here, this is F1. Is so 3 and 22.4. What is that? Let me write this as L. So L is square root of that, right? Supposed to be 1.92 something, right? Okay. So that L, okay. I will write the final results. You can just check the numbers, whether it is correct or not. So this will be W and then 4.8 meter. And minus, this will be F1 1.2 over 1.92, right? Yeah, you need to check 3 and 2.4. So this will be F1 1.2 1.92 6 meter. Okay, this is equal 0. So we get everything from here. This will be, we get around 3.75. So we get F1 is, after calculations, this is 1.28 W. I think most of you get correct here, right? And then since we have this F1, then we could definitely get the AX and AY. So AX is getting from or perhaps this is not going to be here. Let's just assume that they are going to be that. So AX will be 1.2, 1.92 F1, or around 0.8 W, and AY and sometimes the numbers that I choose is the round has been rounded in decimals. And similarly, we could take everything here from the CX. We could get from the another equilibrium. So CX plus AX equals 0. So CX will be 0.8 and the for the vertical, cy minus y minus the ay or plus ay equals 0. So this will be cy is 2w. Okay. So the final result for the first question would be and I think this is something that most of you forget to write. So this will be 0.8 W, but you can give the directions like this. And then AY is W and then go down. And CX is 0.8 W going to the right. CY 2W upwards like that. Okay, since we have the F1 already, then the other two forces that we need to know is the F2 and F3. F2 and F3, they are both in the intersection of the point C. So I think we can localize this and describe in one diagram. So suppose that this is the CX. So let's say this is the C. So we have the F2 and we have here is F3. This is CX is 0.8. It's 2W for CY, right? And based on just a local equilibrium within this point C, we could get everything. So suppose that we take the horizontal axis, okay, to get the F3. And with the same triangle, we get 1.2, 1.92 F3 plus 0.8 W equals 0. So F3 will be negative 1.28 W. Okay. The same thing with the F2, we can take the vertical axis. So this will be 1.5 F3 plus F2 plus 2W equals 0. So after calculation here, this will result in negative. Well, of course, some may be rounded decimals as maybe 0.9. It's okay, it's still okay. But I will just make it into rounded into 1, okay, just to make it easy to see. And don't forget, every time we have all the forces, we need to mention what kind of force they will have. So that's the final products. The F1 is 1.28 W. This is tension for the positive signs. F2 will be W, but it's negative sign, so this should be compressed. And F3 will be 1.28, but it's negative, so it should be compressions. Okay. Okay, so that's number one. And let's move to number two. Okay, so we have two weights attached by cables to the beam BE. And then we have pin B and then pin A also fixed. So, and we have all the distances through all the points. We need to determine the tension in cable AD and determine the reaction force at pin B. And the second question is the internal resultance at the cross section C. And we have to write all the answers in terms of W. Now, if we, before we taken this into our calculations, if we see the AD, this is going to make a proportional triangle. We have 3 over 8 L, and we have this L over 4, L over 4, 2 over 4, which is proportional. So we have 3, 4, 5 triangles. So this will be so 3 over 8. This is L over 2, but I will multiply by 4, so 4 over 8 L. So this should be 5 over 8 L, right? So we have 3, 4, 5 triangle to help navigate the trigonometry. Okay. So we have now, since we take this triangle as our approach, and then we would like to know the tension at AD, right? So we could take because we have all descriptions here. So we could take this BE as our main frame, and taking all this tension as we can take this as a force. This is also another force here, and we can take B as our perspective to be take as a moment. So we take the moment from E, from B, and from A, and so let me write here for the first question A, we take the moment with respect to B equals 0. And then take the clockwise as a positive. So LW plus or WL, or maybe just LW, and then plus the L over 2 and then we say that if we take this in terms of this part here, which is, this is going to be, let's say this is TAD. So we can have both, so theta is here. So this will be TAD sign, right? 3/5. And then the distance is L/2, right? So we can write here, and since this is going to be counterclockwise, this is negative 3/5 DAD multiplied with L/2 equals 0. And we can solve everything here, right? We can cancel all the L. And then we can write DAD 3/10 is 2W, right? So DAD is 20 divided by 3 is 6.66 or 7W. Okay. So this is DAD. And then the second, we need to also determine the force at pin B. So at pin B, we could take this as we have Bx and By. So taking the sigma force for the vertical axis, we could take the By plus DAD is equal to W plus W, or 3W. Oh, this is 3/5, sorry, 3/5, so plus. And then this equals 0, and calculate everything here. This will be equal to around negative W. And then taking the horizontal axis for Bx, this is going to be equal to 4/5 DAD, which is 5.333W. Okay, so we get everything for the first question. And the second question is the internal force at the C, right? Cross section C. So at cross section C, I think we can describe this in this picture. This is C, this is B, and we have, this is the shear force, the normal force here, and the moment. And then at pin B, we have described the By and Bx. I think I need to check this. Is this correct answer? .666 3.996 W plus 3. Oh, this should be minus. Sorry, should be minus. Should be minus 3. Yeah, 0.99. Yeah, some of you I think answer in 0.99, right? I think it's really okay, but I will round it as 1. to make it easy. And you can do that in your exam as well. So you can have, like for example, you have 6.9, you would like to have like a 7, it's okay. That's okay. All right, so we can have this. This will be 5.33W. This will be W, right? Okay. So from here we could get the normal force directly, which is negative 5.33W, and phi C is going to be equal to negative Vy, or phi C is equal W. And then the moment, if we take with respect to C, we get, this is how much? L over 4. Distance is L over 4. So W, L over 4. Let me write the clockwise as positive. So this will be negative and then negative. So this will be negative. Okay, so we get everything. FC is 5.33W, but since we get negative, so we write compressions. Phi C is positive, and M, the moment, is negative. Or if you want to write with the positive value, we can say it will have that directions. Or maybe just skipping negative, I think it should be okay. We will be confusing if you write the rotations. Maybe just this should be okay. Okay, maybe the last question, but I think, because I assume that we only have several minutes to take these two questions, I haven't prepared the third one, but I will just draw the diagrams for the third questions. I hope that is okay. I will complete everything as our final notes later, okay, tomorrow, okay, after we have exercise again tomorrow, okay. So next week will be midterm, right? The Monday, okay, Monday, 2 hours, okay. So let me get the third questions. So the third questions is, let me draw very quickly. This is A, D, and then we have a distribution force. We call this as a W0 or WO. And then we have a point here, B and C. At this end, the end points of the distributions, we have C. And then all will be the same distance in between, L over 3. So we have a roller support in D. This is roller support, which means that if we want to make the diagram, let me make again here, that for A we have AX and AY, And for the d, we have only dy. And then let me just make another triangle here, just to give you an idea that we have a distribution here, but I will write the final or the resultants for this triangle. So the triangle will have the resultants on 2/3 to the right, to the center will be here. So if this is going to be 2/3, so this is going to be 2/3, this is L, then we have divide this by 3 again. So we have here, this will be another distances. So we have here will be our resultants, which is so this will be or let me write here. Let me write on the here. So we are going to have 2/3 by 2/3. So this will be 4/9 L. Okay. And this will be one over 3 by 2/3. So 2/9, right? And we have another L/3 here. And we could say this 2 can be taken as 1 as 5/9 L. Okay. And this will be half. So half multiply with the base and height. So the base will be 2/3 L. Or let me take it down to make it. So this will be equal 1/3 WOL. Okay, that's the resultants. Okay. Okay, I think we get everything for now. So we can take the reactions at A and D. Suppose that first we can take with respect to A, and we can take the respect for D for the moment. So let's start from the D first. And taking that as our positive. So AY L, right? And minus this resultant from the distributions, and then multiply with 5/9 L. This is equal 0. So we get L is cancelled here, so we have only one L. So AY will be 5/27, right? And the same thing here, we get the moment with respect to A. So this will be positive to 4/9 L, right? And then minus DYL. So we get dy is 4/27. Okay. And of course the AX will be 0 because there's nothing on the horizontal axis. So there's no equilibrium for the horizontal. And then at the cross sections B, we need to take the internal reactions or internal forces. So B is at the L over 3. So let's say we have so to suppose that this is B, this is A, so we have AX, we have AY, and what we need to do is we need to make another distribution force. Okay, or let me just write the final resultants. Now it's L over 3, right? So now it's L over 3, the total distances. So we are going to have a 2 over 3 of L over 3. So this will be 2 over 9. Maybe around there. So this is 2 over 9L. This will be 1 over 9L, right? And this will be the same WO, but this will be equal to half multiplied 2 over 9L WO and this is not this is not WO, right? This is precisely so if we take this as a triangle, the ratio of triangle, so we write here WO over 2 over 3L is equal to, let's say, Y over L over 3. So I can get on everything here. So we have that Y is WO over 2. So this will be WO over 2. So don't forget that. This is WO over 2. So this resultant will be 2 over 9 L multiplied with half WO over 2. Okay, we can continue this tomorrow, okay?